The SPICE simulation, we will quickly go over the SPICE. This is the outline. So we'll see what is SPICE, and there are several simulation options. So DC analysis and transient analysis. These are two most popular. In digital, that is good enough. But for analog circuit designer, you may need additional different variety of the simulation mode. We need to understand what is a sub-circuit and how we optimize this. How we optimize the circuit and how we measure the power, so we can compare some logical effort from the simulation result. The SPICE is the abbreviation of a simulation program with integrated circuit emphasis that is originally developed in 1970s at Berkeley. So many commercial versions are there. So in our lab, we mostly use the Spectre from the Cadence. The lec7Spice is robust, the most popular. Now the Spectre is also widely used. The lec7Spice is supported by Synopsys. The company name is Synopsys. The Cadence supports the Spectres. So the old days that was written in Fortran for punch card machines, but nowadays we don't do that. So sometimes we call circuit elements called cards, but this is a kind of old term. So we will usually we use the SPICE stack is kind of the written description of the circuit. That is called SPICE stack. We often this is about how you write the device SPICE stack, and it is like writing a program. First you have to plan to sketch. This is the planning stage and actual coding stage and testing stage there. So first you sketch schematic on paper or in editor using GUI. And most of the GUI program you are using just give lots of the easiness for writing or drawing a circuit. Once the circuit is drawn, we need to generate the actual netlist by coding or automatically generate by the program software. In case you want to write a code, you start with you put some generous comments there, and then when you test, you just predict what the result should be, right? Instead of checking what the result will be. So output, the purpose of the simulation is checking the result versus what you expect. Without expectation, the result from simulation seems like a garbage, because you may put in the garbage, so you may expect the garbage out. So always it is important, always when you test a circuit using simulator, you must have some concept of what the result will be. Whether that result is expected or not, you need to determine, you must decipher what the simulator result, right, is. So that's the most of the student making a mistake. They trying to get the sum. They rely on the simulation too much, because In such case, student may set up the simulation environment not properly, right? So you have to be aware of what the result should be before you actually simulate. This is an example of a SPICE deck. We have a simple voltage source here and resistor and capacitance. So we have 3 components in network, so we define 1, 2, 3. First one is the module name here, and this is a net definition. So in is this net name of the net, and GND is the name of net here. PWL in input and output. This is the instance name, and this is the module, the sub-circuit name. So we use the PWL with the instance name of a VIN. So this is instance name, all instance name. So R1, RC1, and VIN, and these are the net name, right? So this is the property of the resistance, 2K and 100 femtofarad of the C1. So according to this, we know that this node is in and this node is GND and this is out. So each node we define the net name here. So we have 3 components here. So VIN is defined as the PWL, that is piecewise linear voltage source. At 0 picosecond, at time 0 we have a 0 voltage, and time 100 picosecond we get the 0, and time 150 picosecond we have a 1.8. So you connect them, you get this kind of waveform there. This is the 100 pico, and this is 0.150 picosecond, and we add the 800 picosecond, we stay. This is the result of the y-axis is kind of time. We get the output shown here like this. Kind of a behavior is we get. For the input, we see the A like this. Input comes in and output comes out, something like that. So this is kind of an example of the output. So simple RC circuit. This interface is a very old time output. So nowadays we have a more beautiful output plot rather than like this, right? This is just an example. Shown here is a graphical output. As you can see, we have input coming in and the output comes like RC network. Sources. There are a different variety of the sources defined in the simulation. We have for example, we have a DC source defined like this. You start with the character V,
and this is the name of the nodes and the value property of the DC voltage, that is 2.5 volt. We also have a piecewise linear source called PWL. So we define PWL with the instance name of the Vin. Between input and ground node, we have all the piecewise voltage information on the right. Okay, we can have also pulse the source. This is pulse is the keyword that we say that this is pulse the source. This is the name of the voltage. Pulse the source, instance name, right? Instance name. This is net name between two nets. Right hand side is the kind of property. So for example, for pulse we defined like V1 and V2 and TD and rise time and fall time and pulse width, etc. like this. So we define these value on the right and then define V1 and V2 here, right? So this is a kind of a pulse. PER is a period of the pulse, right? So we define also period here. We can repeat this pulse with the period argument here. This is just example that used in actual lec7Spice here. There are a variety of the SpiceNet elements. We want to represent all kind of electrical components, resistor, capacitor, inductor, and etc. Right? All these letters represent each elements. elements defined with the M element, the M with the name, and drain gate source node and body and each type, whether that is PMOS or NMOS. And also we have a WL definition and area of the source. AS is area of the source, AD is area of the drain, PS is perimeter of the source and perimeter of the drain. All these are described, right? So you can, and this actually define the characteristic of the transitions. This is a transient analysis within including MOSFET design. We have a input and NMOS and PMOS. We have a also supply voltage VDD here. So we have 4 instances here, 1, 2, 3, 4. Each one, this is VDD and this is the input, and the transistor M1 and M2. Right? So we are using the transient with the 1 picosecond time step for duration of 200 picosecond. Right? The output, you see, like this kind of a pulse input, you get the overshoot like this, right? This overshoot comes from the input output parasitic, so parasitic capacitance there. Because of this feed forward capacitance, we get this some of the input a sharp, edgy. Whenever input changes sharply, the output will follow the input, right, momentarily. This is very fast edge. For that case, you get this kind of glitches.